Hi everyone. In this video we are discussing the secondary forces. In the previous videos we have seen the different types of primary forces or primary bonds, which were ionic bonds, covalent bonds, coordinate bonds and metallic bonds. Those are strong interactions existing between atoms. But in the case of secondary forces, we cannot call them as bonds. Rather, they are attractive interactions, weak intermolecular interactions which hold the atoms or molecules together. They are called secondary forces. So we can say atoms or molecules are held together by weak interaction other than primary bonds, and they are called secondary forces. The various types of secondary forces are ion-dipole interactions, dipole-dipole interactions, ion-induced dipole interactions, dipole-induced dipole interactions, and finally induced dipole interactions or van der Waals interactions. Now let's see each one in detail. First of all, ion-dipole interactions. As the name indicates, these interactions arises because of attractive forces that results from the electrostatic interaction between an ion and a neutral molecule that has a dipole. That means, let's take an example. Sodium chloride, when it is dissolved in water, the interaction or the factor favoring the dissolution of the ionic compound is the ion-dipole interaction between sodium and chloride ions with dipole of water. We know each ion, the cation and anions, are attracted by the dipole of water. Water molecule is having permanent polarity and it is having a dipole moment. So the positive part of the dipole attracts the anion and the negative part of the dipole attracts the cation. And this sort of ion-dipole interaction facilitates the dissolution of the ionic compound in the polar solvent. So we can generally say the ion-dipole interactions are responsible for solvation of ions by polar solvents and or dissolution of ionic substances in water. The second type is dipole-dipole interaction. So these dipole-dipole forces are attractive forces between positive end of one polar molecule and the negative end of another polar molecule. We can take the typical example of hydrogen bonding. That is the best example for a dipole-dipole interaction. We know a hydrogen bond is formed between or formed by the attraction between hydrogen of one molecule with electronegative element of another molecule or even the same molecule. So here the dipole moment is responsible for this attraction. The positive end of the dipole of one molecule interacts with the negative end of the dipole of another molecule, and this interaction results in the association between the molecules. So the magnitude or the extent of this type of interaction depends upon the dipole moment of the molecule. Higher the dipole moment, more strong would be the dipole-dipole interaction. The third type of secondary force is called the ion-induced dipole interaction. So as the name indicates, here the attraction arises when an ion approaches a non-polar molecule and induces a dipole in the non-polar molecule by disturbing the electron cloud of the non-polar species. So here also we can see this example. We can illustrate with this example the formation of triiodide molecule from iodine molecule and I minus ion from the interaction between I minus and I2. So here you can recollect the electromeric effect that we studied in organic chemistry. By the approach of a charged species, there will be disturbance in the electron distribution of the non-polar molecule. We know iodine molecule as such is non-polar. There is equal distribution of electron density in between the two atoms. But by the approach of this I minus ion, there will be a difference in the electron distribution. Or we can say when this I minus approaches the iodine molecule, there will be repulsion of electrons, and these electrons clouds are located at one part of, or they are now shifted to one part of the molecule, and we can have a temporary polarity or an instantaneous dipole is developed within this molecule by the approach of this charged species. So this molecule, the initially non-polar iodine molecule develops a temporary polarity as delta plus and delta minus on each iodine atom. So this dipole, induced dipole, now associate with the I minus ion, the charged or the ion, and the interaction, that ion induced dipole interaction, will result in the association of the species as a triiodide ion. So this sort of interaction between an ion and an instantaneous or induced dipole is called ion-induced dipole interaction. Next type is called the dipole-induced dipole interaction. This is also just similar to the ion-induced dipole interaction we discussed just now. Only difference is, in the case of ion-dipole interaction, an ion is inducing dipole moment, whereas here a polar molecule or a dipole itself is creating or inducing dipole moment in a non-polar species. So we can say this is a weak attraction arises when a polar molecule induces a dipole in a non-polar molecule by disturbing the electron distribution in the non-polar species. So this is not much common compared to other type of secondary forces. Here we can see a permanent dipole molecule. This can induce temporary polarity or instantaneous dipole in a non-polar molecule. By the approach of this dipole polar molecule, there can be an induced dipole, or the electron density can be disturbed, and that result in an induced dipole in the non-polar molecule. And now this permanent dipole and induced dipole interact each other, and that result in an attraction which is called dipole-induced dipole interaction. So example for this type of interaction is formation of certain hydrates of inert gases. We know hydrates means the water of hydration. So it is water molecule is a polar molecule, so that induces dipole moment in a non-polar species. The last type of secondary forces is called the induced dipole interaction. This is otherwise called the London dispersion forces or van der Waals forces. So these type of interactions are existing in non-polar molecules. Non-polar molecules such as say I2, Cl2, etc. So we can say the London dispersion force is a temporary attractive force that results when electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. So this can exist in different atoms or in different molecules, or we can say generally non-polar species. These attractive forces cause non-polar substances to condense to liquids and to freeze into solids when the temperature is lowered sufficiently. So we can explain with the example of say iodine molecule. You know, iodine molecule is a non-polar molecule, and as such there is no chance of polarity in the molecule. But at some times the movement or circulation of electrons around the atoms can happen in such a way that at a particular instant of time the electron density will be shifted to one part of the molecule. So there occurs a slight negative charge and a slight positive charge on the other end. That means an instantaneous dipole is developed for a very short period of time. So this instantaneous dipole immediately induces dipole in the neighboring molecule. So the neighboring molecule also we know it is non-polar, So as such, initially the molecule is non-polar, but the development of instantaneous dipole for a very short period of time induces dipole moment in the neighboring molecule also. And this instantaneous dipole is developed due to the unequal distribution or due to the circulation of electron clouds. So this type of temporary polarity or temporary polarity development, or that is called the induced dipole moment, and this exists for a very short period of time and it immediately stops. And at the same time, again the electron distribution, the circulation of electron again can create a similar induced dipole moment, and it again vanishes easily. So this is we can say this is a very weak interaction, and this type of interaction is called induced dipole interaction. That means a nonpolar molecule develops an instantaneous dipole and it induces dipole in the neighboring molecule also. And these are associated by this induced dipole interaction. And these interactions are called London forces or van der Waals forces. So these are the different types of secondary forces. So we have discussed ion-dipole interaction, dipole-dipole interaction, ion-induced dipole interaction, dipole-induced dipole interaction, and finally induced dipole interaction. Next we can discuss about hydrogen bonding. We know hydrogen bonding, even though it is a type of dipole-dipole interaction, it is a very important type of secondary forces which is very common in many molecules. So hydrogen bond is the attraction, or it is the attractive interaction between hydrogen of one molecule with electronegative element of another or the same molecule. And the magnitude of hydrogen bonding depends upon the dipole moment of the molecule. We have mainly two types of hydrogen bonding. One is called intermolecular hydrogen bonding and other is intramolecular hydrogen bonding. So the given example here is an intermolecular hydrogen bonding. As the name indicates, this is the hydrogen bonding resulting from the attraction between hydrogen of one molecule with electronegative element of another molecule. So here it is attraction between different molecules. For example, the hydrogen bond existing in water molecule, or the hydrogen bond existing between water and alcohol molecule, or another example as is shown in the figure, the hydrogen bond in para-nitrophenol. So in para-nitrophenol, the OH and NO2 functional groups, they are not close enough and these are hence connected, like one OH of one molecule is connected to nitro group of another molecule through intermolecular hydrogen bonding. The second type is called intramolecular hydrogen bonding. The intramolecular hydrogen bonding resulting from attraction between hydrogen of one molecule with electronegative element of the same molecule. The typical example is the hydrogen bonding in orthonitrophenol. We can see that in the case of orthonitrophenol, the OH group and NO2 group are in adjacent position, and this their position facilitates the formation of intramolecular hydrogen bonding. So the molecule, within the molecule there is hydrogen bonding, and such a hydrogen bonding is called intramolecular hydrogen bonding. Now let's see the consequence of hydrogen bonding. First of all, we know the boiling point of water, ammonia, HF, etc. are very high, and the high boiling point of these molecules are due to the existence of strong intermolecular hydrogen bonding between the molecules. So whenever there is intermolecular association between two molecules, there will be close association. They will be closely associated. So we need to provide high temperature in order to separate them, or in order to separate this association. and hence what happens, the boiling point of the system will be raised. So that is one of the consequences of hydrogen bonding. Intermolecular hydrogen bonding results in an increase in the boiling point. And secondly, we know water is a liquid while H2S is a gas. We know H2O and H2S. In both cases, the central element belong to the same group, oxygen and sulfur. But these two have entirely different properties. Water is existing in a liquid form while hydrogen sulfide is in the gaseous form. This is because of the absence of hydrogen bonding, lack of hydrogen bonding in H2S. We know oxygen is highly electronegative, and because of this electronegativity it can make hydrogen bonds. Whereas in the case of H2S, the sulfur is less electronegative, and we can say there is very less amount or almost no hydrogen bonding in the case of H2S. And because of the lack of this hydrogen bonding interaction, there is no association between H2S and it exists in the gaseous form. So all these are due to the strong intermolecular hydrogen bonding. Another consequence is the density of ice is less than that of water. So this is a very common observation. All of us know ice is less denser than water. This is because in ice it is having a solid structure, so regular crystal structure it is having, and in the solid state the oxygen atom is capable of forming two normal covalent bonds as well as two hydrogen bonds. So there is the existence of strong hydrogen bond in the solid state because of the ordered arrangement. So this existence of two additional hydrogen bond will give the water molecule or ice a tetrahedral cage-like structure. We cannot say it is exactly tetrahedral structure, but it is having because of the presence of hydrogen bonds, even though they are not strong as a covalent bond, still the presence of two hydrogen bonds and two normal covalent bonds give water molecule a tetrahedral cage-like structure. And we know the tetrahedral cage-like structure means it occupies more volume, and hence the density of ice is less than that of water. So this is another consequence of hydrogen bonding. Another one is that is another consequence of hydrogen bonding is water contracts when heated from 0 degrees Celsius to 4 degrees Celsius. So this is exactly because of the same reason we explained just now. We know water at 0 degree means it is in the ice form, and at 0 degree it is having a tetrahedral cage-like structure. And the importance of the statement is that we know usually when we heat a substance, what happens is expansion, not contraction. Whereas for water molecule, upon heating from 0 degree to 4 degree, in this small range of temperature, there occurs contraction rather than expansion. And this is due to the presence of tetrahedral cage-like structure. We know at 0 degree water is having a cage-like structure. So when you heat water from 0 degree up to 4 degree, what happens is all the cage-like structure, all the hydrogen bonds will be broken. So when the hydrogen bonds are broken, what happens? The cage-like structure will be lost. So there will be now the volume occupied will be less. So that means there occurs contraction rather than expansion. So up to 4 degree, all the hydrogen bonds will be broken. Now after 4 degree, when it is heated, there occurs normal expansion process. So the contraction at a temperature, on increasing temperature from 0 degree to 4 degree is due to the breakdown of the tetrahedral cage-like structure, and as a result of this breakdown the volume decreases. So that result in a contraction effect. Another consequence is we know acetic acid exists as a dimer. And this is also because of the strong intermolecular hydrogen bond between two acetic acid molecules. So when you take acetic acid molecule in a concentrated sample, it is always existing in the dimeric form. Two acetic acid molecules are associated through two hydrogen bonds between them. But if we dilute the compound, if we dilute the concentrated acetic acid, the hydrogen bonds will be broken and it exists in the monomeric form. So these are the different consequences of hydrogen bonding. So we have seen the different types of secondary forces and some details of hydrogen bonding. What is the definition of hydrogen bonding? The various types, intermolecular and intramolecular types of hydrogen bonding and consequence of hydrogen bonding. So these are all the different types of secondary forces. Thank you all.